I'm Kodama in RIKEN. I will talk about evaluation of SPEC CPU and SPEC OMP on A64FX. This is the outline of my talk. First, I will introduce FUNAC and the processor Fujitsu A64FX. Next, I will summarize SPEC benchmark. Then I will show the result of SPEC benchmark on A64FX. After that, move to discussion and show the several analyses for the result, such as effect of SVE, comparison with Gnu Compiler, and comparison by number of threads. Last, I will conclude my talk. FUNAC is the next generation flagship supercomputer in Japan. RIKEN developed FUNAC along with Fujitsu. The public service of FUNAC started on March this year. Please show the information about FUNAC from this URL. FUNAC consists of 432 racks and totally over 150,000 nodes. The peak performance in normal mode running at 2 GHz is lower than half exaflops, but using boost mode at 2.2 GHz, it becomes more than half exaflops. FUNAC took first place in multiple supercomputing rankings recently announced at ISC21 and SC2020, such as Top 500, HPCG, HPLAI, and Graph 500. The processor of FUNAC is the Fujitsu A64FX. It is ARM-based processor and is the first processor to support SVE, scalable vector extension. In A64FX, two SIMD pipelines of 512-bit are implemented. The A64FX is a many-core processor and consists of 48 compute cores, and internally it is divided into 4 CMGs, core memory groups. That is a NUMA domain, and CMGs are connected by a bidirectional ring bus and support cache coherence between CMGs. A CMG consists of 12 compute core, an assistant core, a shared L2 cache, and a memory controller. As for the main memory, 4 HBM2 stacks are installed in the CPU package. The capacity is 32 GB and throughput is 1 TB per second on chip totally. In addition, a network controller and a PCI Express controller are also implemented on the chip. The internode network is a 6-dimensional mesh torus network called the TOF Interconnect D, following the configuration of the K computer. Detailed microarchitecture is opened in the GitHub. SPEC is a famous benchmark suite for computer systems. It was founded in 1988, more than 30 years ago. SPEC has many types of benchmarks. The performance of SPEC is indexed by ratio, which is relative performance compared to the reference machine, and the total index is the geometric mean of each benchmark ratio. These are attributes, base and peak. In base, all the benchmarks use the same compiler option, while in peak, each benchmark can select the best option. For SPEC CPU, another attribute exists, speed and rate. Speed evaluates the single task performance where thread parallelism is possible, and rate evaluates the multitasking throughput. Here, base speed is only evaluated. First, I will summarize the execution environment for SPEC on A64FX. We use latest Fujitsu compiler of this version and use Clang mode in C and C++ because it is better compatibility for open source programs. The optimization flags are shown here, but only for SPEC CPU int, we added this flag because without the flag, the result check was failed in some benchmarks. This flag slightly limits the optimization, so the result passed the check and the impact for performance was small. We run benchmark in normal mode of 2 GHz. with setting of these environment variables. The first environment variable, paging policy, controls the timing of memory allocation. By default, memory allocation is performed when the program is loaded. For multi-threaded execution across multiple CMGs, it is necessary to set this variable to allocate on demand. That is the first touch policy. The second environment variable, arena lock type, controls the method of memory pool between threads. By default, a common memory pool is used between threads. When memory allocations are frequently requested within threads, it is necessary to set the variable to use independent memory pool for each thread. In addition, we run benchmark with reportable option, but it is reported as invalid run due to defect in the verification of compiler options. However, this is just a matter of writing flag URL. Compiler options themselves are valid, and the check of the execution result was passed, and we think results are valid. This is the result of SPEC CPU-based integer speed for each benchmarks and total index. Here, we compare the performance with Xeon system listed in SPEC web page. Xeon system has dual-socket 24-core Skylake with the same total number of cores as the A64FX, which run on 2.7 GHz, enabling turbo boost with Intel compiler. Almost benchmarks run on single thread, and the performance of A64FX is less than a quarter of the Xeon. The reason for the low performance of A64FX is that the SIMD rate is low in SPEC CPU int, and the frequency and the O3 resources are limited for the throughput-oriented architecture. This is the result of SPEC CPU FP base speed. It also compared with the same Xeon system. When compared with the same number of threads, A64FX is about 60% of the Xeon, but compared with single socket, A64FX is higher. Unlike SPEC CPU int, FP has a large performance difference for each benchmarks. For example, in 619 LBM, A64FX is 70% faster than Xeon. A good benchmark for A64FX may be thanks to its high memory bandwidth. This is the result of SPEC OMP. In the SPEC webpage, there is no system that uses 48 cores of latest Xeon, so we compared with 28 cores in a socket cascade-like system where hyperthread is on. So the number of total threads is 56. The overall performance of A64FX is about 60% of the Xeon. The performance difference between benchmarks is large. In 363 swim, A64FX is 6 times faster. I will check the reason later. In 350 MD, Xeon is 20 times faster than A64FX. This is because the innermost loop was not synchronized in A64FX. We confirmed that it will be 8 times faster by source code tuning, but it is not applicable by current compiler. We hope that it will be applied automatically by improving the compiler. Let's move to discussions. At first, we evaluated the effect of SVE. All the previous results are the result of enabling SVE. We compared them with the result of disabling SVE. In the figure, the performance SVE is shown as a relative value to the performance when SVE is disabled. So, higher value means that SVE was effective. In SPEC CPU int, the maximum effect of SVE is about 20%, and the total score is only 3%. In SPEC CPU FP, the maximum effect is 90% and the total score is 22%, but we expected the further compiler optimization by SVE. In SPEC OMP, the maximum effect is 2.3 times, but the total score is only 12%. This is because enabling SVE results in poor performance in some benchmarks. When SVE is enabled, gather scatter instructions are used, and sometimes it reduces the performance. It is expected that the optimization by the compiler will be applied only when it is effective. The difference between compilers is also evaluated. The previous result was the result by the Fujitsu compiler. Here, we compare it with the evaluation by Gnu Compiler. At AHUG, Gnu Compiler 10.2 can be used after you run this SPEC load command. These flags are used for Gnu Compiler in SPEC. However, in SPEC OMP, LTO link time optimization is omitted because when LTO is specified, the build failed in some benchmarks, and LTO had almost no effect even in the applicable benchmark in SPEC OMP. In the figure, the performance of Fujitsu compiler is shown as a relative value to the performance of Gnu Compiler. In SPEC CPU int, Gnu Compiler has higher performance by about 10% in total score. With Gnu Compiler, the effect of LTO was large, a maximum improvement is 35% and the total improvement is 8%. With Fujitsu compiler, LTO also improved performance and it was almost as same as Gnu Compiler in total. In SPEC CPU FP, 603B waves is 5 times faster than GCC, and in every benchmark, Fujitsu compiler has higher performance than Gnu Compiler, 94% faster in total. In SPEC OMP, in two benchmarks, Gnu Compiler has very low performance while they are not shown here. In total, Fujitsu compiler had 57% better performance. However, excluding these two, the total difference is only 10%. In 360 swim of SPEC OMP, A64FX was 6 times faster than Xeon. We evaluated it by changing the number of threads with 3 types of scheduling: close, scatter, and balance. Close is the default setting, and the previous results are also the result using this. In close, threads are assigned in order from CMG 0, so up to 12 threads are assigned only to CMG 0. In close, the performance is saturated once with 4 threads, the performance gradually decreases to 12 threads, and then the performance improves. For example, of 16 threads, first 12 threads are assigned to CMG 0, and their average bandwidth is about 20 GB per second, while last 4 threads are assigned to CMG 1, and their average bandwidth is 64 GB per second. So, the thread assigned to CMG 1 will be completed fast, but will wait for the thread of CMG 0. Therefore, after exceeding 12 threads, the performance increases in proportion to the increase in the number of threads, not the maximum memory bandwidth. Scatter assigns threads evenly to each CMG in round robin. Balance also assigns threads evenly to each CMG, but it assigned continuously within each CMG. For example, when there are 16 threads, first 4 threads assigned to CMG 0, next 4 threads assigned to CMG 1, and so on. In scatter, the performance improves in proportion to the number of threads up to 12 threads, but after that the performance saturates, and after 24 threads, the performance gradually decreases. Balance have almost the same performance as the scatter. The performance of scatter with 48 threads is about 4% lower than the other two. This is because balance is more like to the shear data in the L2 cache. The maximum performance of balance is at 24 threads, which is 10% higher than at 48 threads. This is because the overheads such as request collision in the memory and L2 cache increase when the number of threads is large. In this way, performance can be improved by optimizing the number of threads and thread scheduling according to the application. However, such optimization for each benchmark is not allowed in base, and it is necessary to show the score as peak. I will conclude my talk. A64FX was evaluated using the SPEC CPU and SPEC OMP benchmarks. SPEC CPU int was lower than Xeon, but SPEC CPU FP was higher than Xeon when evaluated per socket. In SPEC OMP, due to the effect of Xeon's hyperthread, it was about 70% per socket, but some benchmarks greatly exceed Xeon thanks to high memory throughput. Evaluating the effect of SVE, SPEC CPU int had almost no effect, and the SPEC CPU FP and SPEC OMP had a total effect of only 22% and 12%. I hope that the compiler will improve the SIMD conversion rate in the future. Comparison of Fujitsu Compiler and Gnu Compiler. Both compilers have almost the same performance for the SPEC CPU int, but the Fujitsu compiler had better performance for the SPEC CPU FP and SPEC OMP. We also want to evaluate other compilers such as the ARM compiler. Comparison with varying number of threads. The performance is saturated when the number of threads increased in memory-bound programs. In that case, performance can be improved by executing with an appropriate number of threads. We would like to optimize for each benchmark and consider general optimization guidelines. Thank you for attention.